Okay, we were discussing the types of defects, and we said that in order to maximize the strength, we should maximize the linear welding density, but decrease all types of defects. And if you have some preheat treatments or post treatments, let's say, you can decrease this type of defects since they will be quite melted, and these gaps, these voids will be removed, at least some of them. And we have another solution for instance, type 3 defects. If you have a kind of a random or a proper overlap between the foils, you may decrease at least effect of type 3 defects. Since if you have such an overlap, once you have an, let me draw it here. If you have a type 3 defect here, it will not be affecting the strength of your part too much, since underneath of it, we are knowing that we have a solid region and this part is fully filled with material. So the effect of this type 3 defect will not be too much. You may also have random overlap, but you have a higher chance of affecting this, the effect of these type 3 defects more. But if you prefer to use 50% overlap, that will be much better. Let's have a look at the microstructures of these ultrasonic consolidated parts. And we have nickel foils. You can see the bottom layer and the top layer. I think we have kind of an interface right at this point. And you see that it's quite bumpy, but not important since it's not the top layer. Once you are the top layer, you can do an surface machining, do face milling, and increase your surface quality. And the problem here is that sometimes, depending again, as you know, different parameters or oxides or other dust particles you have in between, you may have unbounded regions, and it can be clearly seen if you have a look at the microstructures. This is kind of a modeling. You can see the interface. So I'm once again here. So the interface between the nickel foils. And we have the color of these microstructures depending on their actually orientation. And you can see that we have a pure interface between them. And depending on this color distribution, you can comment about any cracks or other microstructure issues. So what are the main properties of ultrasonic consolidated parts? First of all, obviously, we're going to have anisotropic properties, mechanical properties, since we are, assume that this is again one of the layers. This is a top view of a layer. You might have many foils after each other. You may have one stop here, and then another foil is spread, maybe another one here. And obviously, once you are using sheet metal foils and depositing them on this layer, we will have actually grains in this direction. You'll have longer grains, since probably you're aware of that. These foils, these sheet metals are manufactured with extrusion methods. Once you extrude these foils, you always have longer grains in the direction of extrusion, and probably that will be in this direction, in the direction you are actually depositing the foils. And this will result in actually anisotropic properties. You'll have different strength values in, let's say, X. Assume that this is X direction, we have Y, and in the cross section, you'll obviously have the Z axis, and the strength will be obviously different in these directions. So what do you think? In which direction are you going to have the maximum strength? Yes, your friend, some friends have posted on chat. In X direction, we will have the strongest values. In Y, it will be a bit smaller, and in Z, again, it will be quite low, since in Z, we only have the bonding between the layers. That is the only thing we can say. But in the Z direction, since we have these grains are bonded together, the strength, the maximum strength we can have is in the X axis. And I said extrusion, but it can also be, these foils can also be manufactured with rolling. It doesn't matter. We will always have grains in this X direction. So let's have a look at the which direction is actually the transverse direction. As you see, it is a bit less than the bolt strength. Which direction is the transverse direction? If you consider the previous drawing we have on the previous slide, yes, it's the Y. It's the Y-axis is the transverse direction, and we have usually about 85% of the original strength value. But sometimes your strength in the X-axis or in the longitudinal direction might be a bit higher than the strength of the original material. But as we discussed, in the Z direction, we don't have much strength. It's usually around 50% of the strength of the initial material. So what about ductility? We don't have much ductile products after they are fabricated with ultrasonic consolidation. They are usually less than the ductility values you obtain with the rolling of the pure material. And obviously, since we are putting them on top of each other, we don't have much ductility in the Z direction. So now let's briefly talk about the modeling of ultrasonic consolidation. And we have, as you know, high frequencies. The frequency is at 20 kilohertz. So doing experiments is quite difficult. You cannot easily measure the forces and other things while you are vibrating your sonotrode at these high frequencies. So that's why we are trying to use mostly simulations to understand the fundamentals of this process. So what we do in the simulations, we have combined friction-based and couple-fit models. We have mechanical and thermal models. And once you do the simulations properly, you can see that the temperatures you have at the interfaces are not above the half of actual melting point temperature of the materials, which is actually complying with the experimental results. We said that at the beginning, if you remember, the temperature at the interface is usually around the half of the melting point temperature. So let's have a look at the simple model, simple analytical model. We have our sonotrodes. We have the part underneath. This is our base plate. And we said that, if you remember, we need to apply force to have the welding between the layers. So this is the free body diagram of the parts. We have force applied with the help of sonotrodes. We have the speed of, these are moving actually, and we have some shear forces and force at the interface of the layers. This is the force at the interface, and we have shear force. Now we can talk about the relations between these forces in some minutes. And we are assuming that, first of all, there is no slip between the foil which is being deposited and the sonotrode. So we are properly depositing the material. And the assumption is that the base plate is rigid, it's not moving, it's always stationary. And another assumption is that we only have elastic deformation at the interface of our sonotrodes and the foil which is being deposited. Another assumption, the mechanical properties of all these materials are not being changed during this process. We are assuming that they are all constant. Another assumption, The energy, actually, we are ultrasonic energy, which is generated with the help of the vibration and the amplitude of the vibration, is totally transferred for the bond formation. So we are not using this energy elsewhere in our system. It's just used for joining the sheet metals together. So let's have a look at the motion of the sonotrode first. It's just a vibratory motion. We have an amplitude. We have the frequency. It's 20 kilohertz. So you can simply determine the velocity of it, the acceleration of it, and then you can make use of these in the force equations. We have the shear force and the friction force. These will be, the summation of these are equal to m times the acceleration of our sonotrodes, and you can make use of other variables also. And the thing is that we will be just first considering the single pulse, single motion within the single cycle of our motion. So probably we'll have a kind of an motion, and we will be only considering a single part, and that is the energy actually we are transferring to the sheet metal interface for this pulse. We can calculate by taking the integral between the shear force and by multiplying the shear force with the velocity of our sonotrode, since that will be giving you the power, and if you integrate it, you will obtain the energy transferred to the sheet metal interface. And once you obtain it for a single cycle, then you can multiply it with the number of cycles actually you have in your total motion, and then obtain the total energy you are applying on the metal interfaces. This is how we do the modeling, and you can, after you obtain the total energy, you can check whether this is enough to join the sheet metals together or not. Any questions, guys, about this simple analytical modeling? We're not going into details much, but just giving you the basic idea. We need to determine the energy input for a specific motion, for a specific cycle, and then once you have it, you can multiply with the number of motion cycles you have and obtain the total energy actually displayed on the sheet metal. So now, actually, we are about to finish this chapter. Let's talk about some applications where we can use ultrasonic additive manufacturing or ultrasonic consolidation. First of all, we can make use of it if you want to have special internal features for metallic parts. Since the other additive manufacturing processes, you cannot have internal shapes, internal channels. If you remember, we were always manufacturing solid metal products with the metal additive manufacturing process. But with ultrasonic consolidation or UAM, we can have complex internal features, like we have seen some examples. Some honeycomb structures can be produced, some pipes, or you may have some cavities. We have another important issue. The top surface of these internal features will have stair-step geometry. If you remember, with ultrasonic consolidation in the previous slides, we said that we can eliminate the staircase problem. But right now we are stating that the top surface of these internal features will have a staircase effect, stair-step geometry. Can anyone tell me why we don't have a staircase effect in the underneath niches, but we have staircase effect at the top surface of these internal features? Please unmute yourself and go on.
We can machine the bottom surfaces, but as the cavities close with the top surfaces, we can't machine them.
Yes, our tool actually will not be able to go inside the region. Let me try to illustrate it. Assume that you have a kind of an interface. As we discussed, you can easily machine with the help of a specific tool. You can remove these regions, right? Once you have the proper tool. But if you have a top surface like this one, another top surface, so your tool will not be able to remove these regions. That's why we say that in the top region of your internal features, you will have stair-step geometries. We will for sure have such a geometry at the top region of your internal features. But at least we have internal features. Another issue, we discussed it at the beginning of the lecture today. Once you have a wider, let's say, internal channels, you should be careful about the force you are applying on the sonotrode. If it's too much, then you cannot have a rigid feature. Probably there will be some kind of bending, and your internal features will be modified. You cannot have a perfect shape. So what are the type of materials we are using in ultrasonic consolidation? We may have some brass, aluminum, stainless steel, nickel, copper. They are all possible. And even you may use some composite foils. They can be taped on the metals together, or you can purely use composite tapes. It doesn't matter. So we have high flexibility in terms of materials. Another thing, you can have multi-material structures. In the video we have seen, at the base we have steel, and then at the intermediate portion we have copper, and lastly on top of it again you may have steel foils. So this helps you actually obtain quite functional products. And in addition, you may embed some specific products. If you remember, some wires, some sensors, actuators, batteries even can be embedded into your products. And lastly, you may also have some functionally graded materials. You may have a smooth transition between the, let's say, ceramic foils and the metal products, or between copper and your steel material. These are all possible with the help of ultrasonic consolidation. As I mentioned, we can embed also some fibers or wires. They are all possible. You can have composite fibers between your products, or even optical fibers. And you can have embed such fibers even between dissimilar materials. And what is going to happen is that your fiber will be going into the softer material. You will not be able to go into the harder, but probably you'll have a bit softer material, and your fiber will be joining into that softer material. You may have, obviously, not just composite fibers, carbon fibers. You can also have some ceramic fibers, and you can have these inside your metal matrices. And once you have it, then that means you have a specific part which is actually responding to your requirements. Here we have an example. You see we have silicon carbide fiber. The circular one is silicon carbide fiber, and it's embedded in between aluminum and copper. So you see it's embedded into the aluminum margins. It's softer than copper. That's why it's more into the aluminum material. It's softer and covers the silicon carbide around. So these are all possibilities, all type of applications we can have with ultrasonic consolidation. And further, we said that while you are depositing these layers on top of each other, sometimes you may have smart structures in between. You may have some sensors, you may have actuators, wires, maybe even processors might be embedded into these foils of metals. And this is actually the only additive manufacturing process where you can have where you can produce metals at low temperatures. Other metal products cannot be other metal additive manufacturing processes are doing the operation at very high temperatures. They are melting the powders, if you remember. So you need to reach to the melting point temperature. But in ultrasonic additive manufacturing or ultrasonic consolidation, it is not the case. At low temperatures, you can complete the process. We have an example for smart structures. You see, it's a very complicated product. We have a computational device. It's a processor. We have wiring. We have a sensor. This sensor is connected to the processor. We have antenna underneath. And we have some thermocouple sensing the temperature. And for battery, for power, we have a solar panel underneath. And with the help of this process, ultrasonic consolidation, we can deposit some material, some foils, and then do the consolidation with ultrasonic vibrations and have these products actually embedded into a single unit. So this is an advantage of ultrasonic consolidation. Any questions, guys, we have before we conclude this chapter? Okay, if you don't have any questions, then let's continue with the conclusion. So we have different techniques for sheet lamination. First of all, first one is laminated object manufacturing. If you remember, it was represented as LOM, and we were mainly using papers for that process. And then we have ultrasonic metal welding process, and we use it with the sheet metals and try to obtain complicated products with further machining. Without machining, you cannot have nice products. And all of these processes are quite robust compared to the other ones, other additive manufacturing processes. They are flexible since you can use different materials and also embed some special structures inside, special components inside these products. Another main property of these processes is that we are actually making use of layer-wise additive manufacturing processes. It's a nice advantage since in a shorter time, you can deposit the whole layer. And we do it actually by using point-wise energy source, right? If you think about the sonotrode, we are depositing the foils in a kind of a layer-wise manner, but the energy is deposited in a point-wise manner. And obviously in future, you'll have some other processes related to sheet metal lamination or simply laminated object manufacturing. You'll have many of these in near future.